Hello, Lamai. Today we are starting the unit number 4, chapter 4, the gaseous state of matter. Right, so first of all, let's discuss a bit about the 3 states of matter. Right, normally we have 5 states of matter. Right, in this section, we are normally considering about the major 3 states to begin with. Right, okay. So let's discuss the properties of 3 states of matter, right? Properties of 3 states of matter, right? So we know what are the 3 major states of matter: solid state, right? Solid state, where the particles are closely packed together, right, forming a structure with a definite shape and with a definite volume, is known as the solid state, right? If you have to increase the temperature, if you have to give some more energy to the system, mainly by you can do that by increasing temperature, right? What will happen? The secondary interactions or the bonds between the particles, right, will weaken when you have to apply energy, and the particle starts to move a bit. That state of matter is referred to as the liquid state. The liquid state, where you see some more movements of particles than in the solid state, right? Particles are moving a bit more than the solid state in the liquid state, right? And those are situated a bit away from each other. That is referred to as the liquid state, right? If you have to increase the energy of the system more, basically you can do so by increasing the temperature of the system, so that the bonds between the particles will be broken more severely, and you will come to a state where the particles are freely moving. And the particles are freely moving here and there, like this. And that state of matter is referred to as the gaseous state. Right? These are the 3 major states of matter, right? The solid state, liquid state, and gaseous state. Right? By changing the temperature of the system, by changing the energy of the system, like this, you can convert the solid state to a liquid state or to a gaseous state, right? Even by applying pressure as well, you can do these phase changes. Normally, you can convert the liquid to a solid by decreasing the pressure, and you can you can convert a solid to a liquid by decreasing pressure, as well as you can convert the liquid to a gas by decreasing the pressure, right? So such changes among phases, states of matter, can be done by changing the temperature and the pressure of the system, right? These are the 3 major states of matter. And here we should know the names given to these phase changes as well. The names given to these phase changes or state changes should be known, right? So normally, converting a solid to a liquid is referred to as melting. This process is referred to as melting. Converting a solid to a liquid, melting, right? Okay. and converting a liquid to a gas, that phase change is referred to as the evaporation or vaporization. Evaporation or vaporization. Right? Then converting a gas to a liquid, right, is known as the liquefaction. 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 While converting the liquid to its solid is referred to as solidification, right? Solidification. Solidification. We can convert a solid straightforwardly to a gas without achieving the liquid as well, right? One can convert your solid directly into a gas without achieving the without achieving the liquid state, and that process is referred to as the sublimation. Sublimation. These names given to these phase changes, the state changes should be known, right? Those are normally frequently asked in MCQs, right? So converting a gas directly to a solid without achieving the liquid phase is referred to as the deposition. 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 Right? Normally the sublimation stuff happens when the particles in a solid state are connected via London forces, right? Like I2, the I2 solid, the particles in a solid state are connected via London forces in I2 solid, right? If you are to apply energy to that system, the I2 solid, that absorb energy will break those very weak London forces, and that will put those particles, the I2 particles, apart from each other severely, so that you will achieve the gaseous state without coming to the liquid state. Such a process is referred to as the sublimation. Normally those things happens with the solid phase stuff when the particles are connected via London forces. We can see the sublimation happening with the I2 solid. Even with the CO2 solid, which is also known as the dry ice. You know the dry ice? In those occasions, like in weddings even, you can see the, right, those things with the dry ice. When you put those champagne, right, you will see the smoky thing appears. That thing is done by the dry ice, the solid CO2, which are connected via London forces, right? So when you are to, so no, solid CO2 is at a very low temperature, right? -Celsius temperature. When you apply in those champagne, which is at room temperature, right, then that means the temperature of the dry ice will increase, and that will directly convert to the gaseous state without achieving the liquid state. That is what you see as a smoky thing appearing, right? The dry ice convert into CO2 gas directly. Sublimation. Converting your solid directly to the gas without achieving the liquid phase. Sublimation. Right? Okay. So these kind of depositions also can be seen, right, in the gaseous state, in the gas particles deposit as solids, right? That such things are also can be seen, right? Yeah, even in the I2 gas, you can see this stuff directly depositing, right? Okay, so those are the names. These are the names given to the phase changes. So you should know these things, right? Okay, and as indicated here, these phase changes can be done by changing the temperatures as well as the pressures, right? So that is also clear here, right? So major things we see with the three phases is actually, when it comes to solid phase, the particles are very closely packed to each other. Very limited space between the particles. Among the particles, very limited free space available with the solids. When it comes to gases, among particles, you can see lot of free space is available. Lot of free space is available. And the bonds between the interactions, the attractions among the particles are very less. So those are freely moving here and there, the particles in a gas, not like in a solid. So when it comes to liquid state, right? So the liquid state is actually a situation, the things are in between the solid and the gaseous states, right? The particle movements are less than the particle movements of the gaseous state and greater than the particle movements of the solid state when it comes to liquid state. This free space available among particles is actually less than the gaseous state and greater than the solid state when it comes to liquid state. So that is the state which is in between. The properties are in between those of this gaseous state and the solid state. That is the nature of the liquid state, right? So these phase changes can be done by changing the temperature as well as the pressure, right? Okay, things are clear. No? So these pictures are there at the first point, as the first point of your page number 1, right? Okay, let's discuss the other stuff appearing with the note there. But these are actually all over stuff, Lamai. The things are actually all over stuff. You may have learned all of these stuff at the O levels, right? So I'm just quickly, right, reminding you the ones, the stuff you have learned with the O levels, right? Okay, right. Let's go to the note there. What they are saying, right? So first thing, it is about the arrangement and movement of particles, right? So the note says, right, you can go to the note, it says particles are closely packed, right, in a regular pattern in a solid. When it comes to a gaseous state, it says no regular pattern of particle arrangement, random movements are there, random arrangement of particles. The solid state is actually in between a situation, but anyway, no regular arrangement, the particles can move there, right? So the interparticle distance in a solid space is very less free space available there. Interparticle distance between the particles are very high here, but when it comes to liquid phase, that is in between, the distance between the particles are lesser than the gaseous state and greater than the liquid state. And movement of particles, when it comes to movement of particles, solid state, the particle movements are restricted to vibrations only, right? So normally the kinetic energy of a system is used as 3 forms. A system can use its kinetic energy available as 3 forms of movements, right? The kinetic energy is the energy associated with the movements, no? So such 3 kinds of movements are there to use the kinetic energy of a system. One such a movement is the vibrations. You can use your kinetic energy of your system, of your particles, as vibrations. So vibrate, the particles vibrate like this, vibrations. The second way of movements using the kinetic energy is the rotational movements. So the spinning rotations of particles that will use some of the kinetic energy of system. The third way of using the kinetic energy of system is referred to as the translational moments, right? Particles can move like this, translation moments, right? Those are three methods, three ways of using the kinetic energy available in your system. So when it comes to solids, their movements are restricted to only to the vibrations. Only the vibrations can be seen with these particles. So very limited energy in the system. With very low temperatures, you achieve the solid state. Very limited energy, thermal energy in the system. Low temperatures means very limited thermal energy in the system, and that limited thermal energy is used only to the vibrations of these particles. Only the vibrations are possible as movements to use the kinetic energy of the limited kinetic energy of the system for solids, right? So when it comes to gaseous state, right, particle movements are very heavy. You can clearly see the translation movements here and there. Things happen. The particles are going here and there, freely move. The translation movements are possible, right? So with the liquids also, the translation movements are possible. You see the flow nature of liquids. The particles can move in a liquid as well. So that is what they are saying, right? Movements of particles limited to vibrations in a solid. In a liquid, the free movements of particles are actually in between the that of gaseous state and the solid state. And for gases, the particle moves very fast and freely. Right? The things are clear. The third thing we are considering is about the shape of these three guys. So when it comes to shape, the solid state is coming up with a definite shape. Solid state is coming up with a definite shape, right? So even though your container is quad like this, you could have a definite shape with your solid like this. It could be as a ball like shape. It has its own shape when it comes to solids. Definite shape with solid state, right? When it comes to liquid state, the liquid matter takes the shape of the container, but only the bottom part of the container. The liquid matter takes the shape of the bottom part of your container, right? But when it comes to gaseous state, it takes the shape of the container, shape of the whole container. Throughout the space available, the gas will spread. Gas particles will spread. So the gaseous matter takes up the shape of the container, takes the shape of the whole container, gaseous matter. When it comes to liquid matter, yes, it takes the shape of the container, but only the bottom part of the container. But when it comes to solid state, it is with a definite shape, its own shape, right? So those things are written there as the shape. Next point, the volume. The volume. What is volume? Volume is the space taken by considering matter. Volume is that, the definition for the volume, right? The space taken by the considering matter is referred to as the volume, right? Space taken by the considering matter is referred to as the volume of that matter, right? So volume. So solid is coming up with some definite volume. Solid coming up with some definite volume. Some definite space will be taken by the matter particles of a solid. Definite volume. When it comes to gaseous state, its volume is not going to be definite. If you are to put these particles, the same three particles, to a smaller volume, smaller container, the volume will be smaller. But if you are to put the same three these gaseous particles, same amount of gaseous particles in a large container, right? Those particles will take a larger volume. The volume of the container is actually achieved by the gases. So volume for gases is not a constant, right? The gases takes the total volume of the container, right? It is not a definite value. It is changing according to the container, right? Okay, that is the situation with the gaseous state. Volume is not a constant. It differs according to the container it contains, right? When it comes to liquid state, the liquid state is with a definite volume. Liquid state is the definite volume. So you may think of a Coke, just think of a Coca-Cola, right? Coke, right? So, if you take a 350 milliliter Coca-Cola, right? So, let's think of that, right? You are with this kind of stuff, Coca-Cola, right? So, bottle is there, right? Let's say to the top, Coca-Cola is there in a 350 milliliter bottle, right? When you are drinking this Coca-Cola, what will happen? Right? The liquid level, the Coca-Cola level will drop, right? That means its volume will drop. Now the volume is less than 350. So you clearly see the volume of the vessel, the volume of the liquid is not going to be same as the volume of the vessel, right? It has a definite volume irrespective of the volume of the container, right? So that is the situation in the liquids. So I am again telling you as a summary, solids are with a definite volume, liquids are with a definite volume, and gaseous state is without a definite volume. It takes the volume of the container, right? Okay, that is the situation with the volume of these three states of matter, right? Then the next point, let's discuss about the density of these stuff, density variations with the solids, liquids and gases. What about the density? Right, density. So what is density, Lama, actually? What is density? Density means, as an equation we can say D is equal to M over V. Density, M over V, mass over volume, right? Density means mass per unit volume. Mass per unit volume. D is equal to M over V, mass per unit volume, right? Greater the mass in a unit volume means your density is high. Greater the mass in unit volume is, that means your density is high. Smaller the mass in a unit volume means the density is low. Right? The idea is clear, no? Mass per unit volume, the density, right? Normally, when it comes to the particles, when it comes to these states of matter, right, more the mass particles are there in a unit volume, your mass will be greater. It's like this, right? Let's think of this, right? Let's think of a kind of situation. So let's take a unit volume like this. In a unit volume, say you have, right, 5 mass particles as well as 5 particles. In this unit volume, say you are with 10 particles. Say one particle is with, right, mass m, here also mass m. So if you are with 5 particles in this unit volume, right, the total mass here is going to be 5m. Total mass is 5m, as 5 particles are there in a unit volume, I just took a unit volume here. If you are with 10 particles with mass m, the total mass here in this unit volume is 10 m, right? So you can clearly see, right, when the number of particles are high in unit volume, like here, the total mass in unit volume is high, right? Number 5 number of particles are here, 10 number of particles are here, more than number of particles in unit volume, the total mass of the unit volume is high. That means the density is high. Mass in a unit volume is referred to as the density. So density is high when you have more particles in unit volume. Density is high when you have more particles in a unit volume, right? Because the concept is clear. Let's apply those concepts, right, to these 3 states of matter, right? Okay, so let's consider a unit volume of a solid. Let's consider this kind of a unit volume of a solid. So you have 4 particles in unit volume. I'll take the same kind of a space in a liquid as well. So you can see only 2 particles in unit volume. So more particles in unit volume can be obtained with the solid state. In unit volume you have only 2 particles here. Here you have 4 particles in unit volume. More particles in unit volume means more mass in unit volume. So density is high in a solid compared to a liquid. What about the gaseous state? Let's take a unit volume like that. Just 1 particle in unit volume. Just 1 particle in unit volume. So the density is very less here. The mass is very less. The density is very low. Right? Here the density is very high. More particles in unit volume means more mass in unit volume. So that means density is high. Mass per unit volume is high. Density is high. Very less amount of particles in unit volume means less mass in unit volume. That means the density is very low with the gaseous state. When it comes to liquid state, it is in between, right? So density variation can be obtained like that. The density is very high with the solid state. The density is very low with the gaseous state. The density is coming up with an in-between value for the liquid state compared to the solid and the gaseous state. If you need some examples, right? If you take this iron, solid iron, right? Its density would be like 7.8 GCM minus 3, 7.8 grams per centimeter cube. When it comes to a liquid like water, right? Its density is almost 1 GCM minus 3, 7.8 to 1. So you clearly see the difference. And when it comes to a gas like H2 gas, kind of a gas, its density is 10 to minus 4 GCM minus 3. That means 0.0001. Very, very small number as a density for gases, right? That is the situation with the density variation for these 3 major states of matter. Clear now? Right. Okay. Next stuff. Let's discuss about the compressibility. The compressibility of these 3 states of matter. Compressibility. What is referred to as the compressibility now? What is referred to as the compressibility? Right? Compressibility. Okay. The compressibility is the ability to decrease the volume of matter by applying the pressure. Ability to decrease the volume of matter by applying pressure is referred to as the compressibility, right? Decreasing the volume by applying pressure, right? So if you can decrease more the volume by applying pressure, we say your compressibility is high. If it is very hard to decrease the volume of your matter by applying pressure, we say the compressibility is low. right? So the compressibility is all about the free space available among molecules. The compressibility is all about the free space available among molecules, right? If you have more space available among molecules like this, if you have more free space available among molecules, we can easily decrease the volume by applying pressure. We can easily apply the pressure and, right, shrink these guys together, and we can decrease the pressure, so decrease the volume of your matter, right? If you have more free space available among molecules, we can apply pressure and shrink the matter easily. So we can say the compressibility is high there. We can decrease the volume greatly by applying pressure if you are with more space, free space available among molecules. So with the gases, the compressibility is very high. Compressibility is very high. As those in gases, very high free space is available among molecules. The opposite is true for solids. The opposite is true for solids. When it comes to solids, the particles are very closely packed to each other. The free space available among particles are very, very limited, very minimal. So by applying pressure, it is very hard to put these guys further closer, because very limited free space is available. It is very hard to decrease the volume here because no free space available. There is limited free space available among molecules, right? So the compressibility, the ability to decrease the volume by applying pressure, is very limited here. So that the compressibility is very low here with the solids. So the liquid state is coming up with some in-between value for the compressibility as well, compared to gaseous state and the solid state, right? The compressibility is kind of in-between value compared to the gaseous state and the solid state for a liquid state, right? Okay, because all about the free space available among particles, right? The free space available among particles is in between the gaseous state and the solid state for the liquid state. That is why the compressibility is in between the gaseous and the solid states for the liquid state, right? That is all about the compressibility variation of these three major states of matter, right? So in your note, it is said, with solids, extremely hard to compress, the compressibility is very low. With gases, it says, can compress to a greater extent, right? When it comes to the liquid, the note says extremely hard to compress. Yes, because the particles are much closely bound. Very limited free space available there as well for the liquid space, right now. So that is the idea. So actually these things have been learned in your O levels as well, right? What I have done was quickly going through those things. We had just done just a quick recap of the things you have learned in your O levels, right? Okay, right. So now onwards, after this session onwards, we'll concentrate only on the gaseous state, right? Only on the gaseous state. This is the major states we have discussed under the chapter 4, right? Let's move to the gaseous state now, right? So If you have been asked to explain a gas, then it is bit more difficult, right, compared to a explanation of a solid or a liquid, right? So if one is asking you to explain a solid, it is much easier, no? Let's see. Let's take this example, right? If one asks you to explain this solid matter, this marker pen, right? Okay, it is not that much hard, right? You can say this solid matter is with black color. You can discuss about its volume as well, right? Its length as well. This amount of length is there, right? The volume as well. How it appears, you see this stuff. The shape can be described with the solid matter. Even with the liquid matter, you can discuss about its volume, its shape, even its color with the liquid matter as well. All those things are possible as you see the liquid matter as well as the solid matter from your naked eye. You clearly see, and you can clearly identify, because you see those two kinds of matter from your naked eye. That is why it is very easy for you to describe a solid or a liquid. But when it comes to gas, as an example, if one is asking you to explain the gas here, so we have gas here, right? Around you, right? The volume is filled up with the atmospheric gas, right? Here you have a gas, here as well. Gas is here. We can see. We can't see, but a gas is there, right? So then, how to explain? How to explain this gaseous stuff? It's not going to be easy, like in a solid as well as in a liquid. Why is that? Because you won't see that, right? It's very hard to see the appearance of gas, even though we see that a gas is there, right? So scientists thought of a model to explain these gases, gaseous phase of matter, gaseous state of matter, right? So with their molecular kinetic theory, they try to explain a gas with use of theories of the molecular kinetic theory. Remember, molecular kinetic theory is not a theory which is concentrating only on the gases, right? The molecular kinetic theory is a theory which concentrates on all the types of matter, solid, liquid, gas, all the stuff. With that theory, under the section of gases, they had came up with some very important points to explain the behavior of these gases, right? So let's discuss those important stuff discussed with the molecular kinetic theory to identify, to have a clear picture of a gas, right? So this section is referred to as the description of a gas according to molecular kinetic theory, right? So let's discuss about that, right? So according to molecular kinetic theory, right? An ideal gas, a perfect gas is explained or picturized as follows, right? So according to molecular kinetic theory, an ideal gas or a perfect gas is explained like this. So normally this is the situation of a perfect gas, ideal gas, right? If we are right coming up with some problems explaining a stuff, right? So first we are trying to simplify. We are trying to simplify and come up with some idea about those stuff. After that, we can do some corrections and come up with the right more perfect stuff, right? So that is what they have done here. First they have discussed of an ideal gas, a perfect gas. So the real gases are a bit more different than this situation, but the first thing they came up with is a situation of an ideal gas. See how these ideal gases are explained according to molecular kinetic theory, right? I'll explain the stuff one by one, and we can write the stuff with the explanation as well, right? After the explanation as well, right? Okay, first thing, the first point. The first point. Point number one. Right? Point number one. The point number one says, right? The gases are, see, you have a gas here. One can say you have a gas here. The point number one says, gases are composed of gas molecules. Gases are composed of gas molecules. Gas molecules. Gases are composed of gas molecules which are moving towards random directions, with random speeds. So movements are random. Here as well, something like this. So gases are composed of gas molecules which are moving in random directions with random speeds. See, I'll write this one a bit larger, right, to have a clear picture. Which are moving in random directions, right? With random speeds. Let's say this is moving with 2 ms minus 1. This will move with 3 ms minus 1, like that. This will move with 10 ms minus 1. This with 7 ms minus 1. Random speeds, right? 2 ms minus 1 again. So the first point is this: the gases are made out of gas molecules which are moving in random directions with different speeds, and those movements are straight line movements, straight line motions. So gases are not moving like this. Gases are not moving like this. Just straight line movements like this, or this. Straight line movements. Straight line movements, not curvy movements, right? So again I'm telling you the first point, right? Gases are made out of gas molecules which are moving in random directions with different speeds, and those movements are actually straight line motions. Right, never. So first, let's write that thing, number 1, right? Let's write this, number 1, right? Gases are composed of, let's put the number 1 and write, gases are composed of widely separated gas particles. Widely separated gas particles. Gases are composed of widely separated gas particles, right? And these particles are in come to the red color and write random within brackets all possible direction close the brackets, random all possible direction close the brackets, comma straight line motions in different directions, in different speeds. Gases are composed of widely separated gas particles, and these particles are in random all possible directions within brackets, right? Straight line motions in different speeds, right? That is the first point of describing a gas, right? Second point. First thing is done, right? Second thing. So I am trying to give you a clear picture of a gas, right? I'm trying to give you a clear picture of a gas, right? Of a gas. Basically of an ideal gas in this case, right? Okay. The second thing. Let's discuss more. Let's describe more about this behavior of these gas molecules, right? Okay, the second thing. The second point is concentrating basically on the shape of this stuff. So, as we won't see the stuff, we are not seeing the particles of the gas now from our naked eye. So one can say these particles are like stars, the shape of stars are there. Or one can say the shape of these molecules are like stars. Or one can say those are like triangles. Or one can say those are like lions, right? Lions are, I don't know how to draw the lion, right? Anyway, lions. Okay, so but there should be a definite shape, right? Okay, so these molecules are not like stars, not like triangles, not like lions or monkeys or any kind of stuff, right? These molecules are actually spherical in shape. That is the second point described by the molecular kinetic theory. Gases are made out of molecules which are moving in random directions with random speeds in straight line motions, right? And those molecules are spherical in shape. Those molecules are spherical in shape, right? These molecules are spherical in shape. Spherically shaped molecules, like this. Molecules are spherical in shape. And then spherical, like balls. When it comes to these spheres, those spheres can be hard spheres as well as very soft spheres. The spheres could be of two types, no? Two extremes are there, no? Hard spheres, like billiard balls. Or spheres could be very soft, like clay balls. So, what kind of a sphere, right, represent these molecules, right? So basically these molecules are referred to as very hard spheres. Molecules of a gas are referred to as very hard spheres, not like clay balls, hard spheres. That is very important. Huh? Molecules of a gas is referred to as hard spheres, rigid spheres, hard spheres. What is the importance of this thing? The hard stuff, that terminology. Hard, rigid. What is the importance of that thing? Let's discuss. Because these gas molecules are considered as hard, rigid spheres, right? The collisions of them, collisions of these gas molecules with the walls of the container, as well as collisions between two gas molecules, are considered as perfectly elastic collisions. Right? Because of these gas molecules are referred to as hard spheres, the collisions between molecules and the walls of the container, as well as the collisions between two molecules, are referred to as perfectly elastic collisions. What are the perfectly elastic collisions? Perfectly elastic collisions are the collisions with no net kinetic energy change. Before collision as well as the after collision comes up with the same net kinetic energy. No change in the total kinetic energy of the system by a collision. Right? Such a collision is referred to as a perfectly elastic collision. Right? So as these guys are considered as hard rigid spheres, the collisions of these molecules are referred to as perfectly elastic collisions. If these guys appear as clay balls, like very soft things, clay balls, you will clearly see if these guys are to get hit to a wall of the container, it is stuck there, right? So the kinetic energy will be totally lost if those are referred to as soft spheres, like clay balls. But that is not what happens. If you are to hit on the walls, that will definitely come back with the same speed without a kinetic energy loss. Right? That is the idea. No net kinetic energy loss during collisions. Right? So that happens because these are referred to as rigid or hard spheres. Right? Another important thing to discuss here, as these are rigid spheres. The second thing which is important to note, that is actually the pressure of the gas. Actually, with this molecular kinetic theory, it is understood the pressure of the gas is due to the collisions of these molecules with the walls of the container. As these guys are rigid spheres, right? When these guys hit these walls of the container, those will insert or exert some force on these walls. That force, if you divide that force inserted by the molecules when they are to hit to these walls of the container, if you divide that force from the total force by the molecules, if you divide that by the total area of the vessel, that will give you the pressure. Of the gas. So the pressure of the gas is due to the collisions of these rigid hard spheres with the walls of the container. Right now? Okay, let's write the second point. The picture is clear. Just write this stuff, right? Okay. Let's write the stuff, right? Number 2. Right? See, just write this. Gas particles, number 2, right? Gas particles, within brackets, molecules, cross the brackets, are Come to red color and write hard spheres. Hard spheres. Hard spheres. Come to the normal color. And undergo, come to red color again, perfectly elastic collisions. Perfectly elastic collisions. Perfectly elastic collisions. Come to the normal color. With other particles or with the walls of the container. With other particles or with the walls of the container. With other particles or with the walls of the container. Right? Write this in the next line under the same point number 2. Write this in with the next line, right? Energy may be transferred from one particle to another. Energy may be transferred from one particle to another. Energy may be transferred from one particle to another, comma. Their individual energies may change. Their individual energies may change. Their individual energies may change. But there is come to red color and write. Come to red color and write. No net loss or gain in kinetic energy. But there is no net loss or gain in kinetic energy. Right? No net loss or gain in kinetic energy. Right? Next point. Under the same point number 2, at the next line, just write. The pressure of the gas, 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 come to the normal color, arises from, the pressure of the gas arises from some of the collisions of, sum means the summation, right? Summation of the collisions of particles with the walls of the container. With the walls of the container. Some of the collisions of particles with the walls of the container. That is how the pressure rises in your gas. Right? Okay. The stuff are clear. So there are two kinds of collisions are possible in a gaseous system. What are the two kinds? One kind is the collisions between particles. The second kind is the collisions between particles and the walls of the container. Out of those two types of collisions, only the second type, the collisions of particles with the walls of the container only leads to the pressure of the gas. The pressure of the gas is due to only the collisions between the particles and the walls of the container. Right? Okay, the idea is clear? Right. Let's come up with the third. Let's try to picturize the third point discussed with the molecular kinetic theory. Third one. Right? Third one. Okay. Next stuff. Actually, if the molecules are like this, if the molecules of a gas are like this, like billiard balls or like this kind of larger rigid spheres, then we would be able to see this stuff. We would be able to see those balls like this appearing with a gas. But actually, we won't see such, no? We won't see such, no? We won't see some kind of balls, kind of things appearing in a gaseous phase, no? Why is that? Because the volume volume of these things are very negligible. The volume of these things are very negligible. So that we say these are not like billiard balls, these are not like marbles, but these hard rigid spheres are actually point masses, point-like masses. So these are considered as point masses. So like this, see, point masses. That is why you won't see these hard rigid balls, point masses. The volume of molecules are negligible. That is what it says actually. That is the picture, right? Okay. These gas molecules are point masses. Point masses means the volume of gas molecules are negligible. Not the mass, right? Not the mass. You have a mass there. Right? Don't come up with that false idea that when the small volume is very negligible, mass is also should be negligible. That is false, right? So even with a very smaller volume, right? Even with a very smaller volume, right? There could be a greater mass with some iron. Even with a smaller volume, you could have a greater mass with iron compared to a larger volume of wool. Compared to larger volume of wool, right? You could have a greater mass in a smaller volume of iron, right? So not always mass and the volume are with a direct relationship. These kind of things also appears, all depending on the density of the stuff, right? So don't have that false idea. As the volume of these gas molecules are negligible, mass is also negligible. No, that is not the case, right? You have a mass, you have a considerable mass, but with a negligible volume. Right? Idea is clear, no? Right. So these hard spheres, those molecules, are considered as point masses. As these are point masses, we can discuss about two observations. What are the two observations? As these are point masses, right? Compared to the distance between two gas molecules, the volume of the gas molecules are negligible. As these guys are point masses, very negligible volume is there, right? Compare the distance between the 2 molecules, the volume of your gas molecules are negligible. That happens due to these are point masses. The second thing, compared to the volume of the gas is the volume of the container, right? Compared to the volume of the gas, the total volume of gas molecules are negligible. So you can put all of these gas molecules in a very little volume, like here. If you were to concentrate all these gas molecules to the corner of the container, it would look like this. Compare total volume of the gas, right? The total volume of the gas molecules are negligible, right? So that is the idea. Both things happens due to the situation of point masses. These are with very negligible volume, right? Just write the third stuff, right? Right. Gas particles are number 3. Gas particles are widely separated. Come to red color and write point masses. Come to the normal color. and therefore the actual volume of the particles is very small, and therefore the actual volume of the particles is very small, within brackets negligible, close the brackets, compared to the volume occupied by the gas, within brackets just write volume of container, close the brackets, right? Write it at the next line. In other words, put a comma, the actual volume of the molecules is negligible in comparison to the empty space between them. This explains the come to the red color and write high compressibility come to the normal color of gases. So compressibility is very high with these gases because free space among gas molecules are very high. That happens because these guys are considered as point masses. These gas molecules are with very negligible volume. That is what it's said as point masses, right now? Okay, this is point number 3. Point number 4. Let's count with point number 4. Let's discuss first of all. Now, as these guys are very small guys, the thing is, compared to the distance between them, the guys are very small. That means it's like if this guy is in Sri Lanka, this is analogous to if this guy is in Sri Lanka, this guy is at normally will be at US, right? The situation is analogous to that, right? If I am at Sri Lanka, right? My friend is at US. Right? This is what this says, right? So compared to the distance between two of us, my size is negligible. Right? That is the idea. No? So that it is very hard to communicate. I can't communicate with a person at US, no? I mean, normally, right? Yeah, you can go for mobile phones and stuff, right? Not like that. As a person, right? We can't communicate like this, no? When I am in Switzerland, Sri Lanka, and my friend when he is in US, right? The situation of these gas molecules are like that. I'm not feeling the presence of my friend, as that guy is very far away from me. I won't see the presence of my friend. I won't feel the presence of my friend. I won't see the presence of my friend. So I can't communicate with him. I can't get attracted to him. I can't get repelled from him. Because the distance is very, very high between two of us. So I can't see him. I can't feel the presence of him due to this situation. So no attractions, no repulsions among myself and my friend. That is the same scenario happens with these gas molecules. This one won't feel the presence of this one. This one won't feel the presence of the other ones. So these gas molecules won't feel the presence of other guys. So that no interactions between the gas molecules. No attractions, no repulsions among gas molecules. Because those guys are very far away from each other and those sizes are negligible. You won't see them, you won't feel them. Right? So we can say no intermolecular attractions or repulsions among gas molecules. Right? Okay. So unless they collide, the gas molecules won't feel the presence of other molecules in the system. Right? Got the idea? No? Right. Just write the stuff. Number 4. Let's write like this. Write in red color. No forces of attraction or repulsion. No forces of attraction or repulsion. No forces of attraction or repulsion. Within brackets. No intermolecular forces. No intermolecular forces. No intermolecular forces. No intermolecular forces. Close the brackets. Come to the normal color. Among gas particles. No intermolecular forces among gas particles. And therefore, come to the red color. And write. Particles of a gas behave independently of one another. Particles of a gas behave independently of one another. Within brackets, unless they collide. In the next line, right? Just write. This postulate explains. Put a comma and come to the next line and write. Dalton's law of partial pressures. Why gases fill their containers entirely. Right? Because of this law, no attractions among particles. So that these particles will fill up the whole space of the container. No attraction. If there were attractions, these guys will attract to each other and shrink. The guys will come closer to each other, so that this kind of stuff is not possible. But as they are not with any attractions among particles, right? So these guys behave independently, going here and there, right? And fill up the whole space of the container. That is why the gases fill up the space of the container entirely. Because no attraction or repulsions, no intermolecular interactions among these particles, right? Okay, that is point number 4. Then write the point number 5. Right? Only 5 points are there. According to molecular kinetic theory, to describe an ideal gas. Let's write that 5. Point number 5, it says the come to red color. Average kinetic energy of gas particles. Depends only on the absolute temperature. depends only on the absolute temperature. The average kinetic energy of gas particles depends only on the absolute temperature, right? So there are some equations. We'll derive these things later in our lesson, not today, but in 2 or 3 weeks time we'll derive these two equations. There are two equations for the average kinetic energy. Right? If you have to consider the average kinetic energy as EK bar, kinetic energy kinetic bar, right? So we can write the average kinetic energy equations like 3O2 RT, right? Per mole of particles, or per mole, let's say per mole, or we can write the same average kinetic energy as 3/2 kBT. This is per molecule, right? This is a constant. R is referred to as the universal gas constant. It's a constant, right? So average kinetic energy depends only on the temperature, right? Only two variables are there: average kinetic energy and the absolute temperature. This is the Kelvin temperature, right? Absolute temperature means the Kelvin temperature. In this case, the Kb means the Boltzmann's constant. Normally constants are denoted as Ks, right? Boltzmann's constant. So the average kinetic energy depends only on the absolute temperature, as these things are a constant. Only two variables: the average kinetic energy and the absolute temperature. So just complete the stuff, right? We'll derive these two guys in 2 weeks time, right? Average kinetic energy of gas molecules depends only on the absolute temperature. These are constants, right? Okay, right? That is all about describing an ideal gas according to the molecular kinetic theory. Right, no? The things are clear. Right. Let's come to the next part, next page of your tune. Page number 3. So that Lamai, right? We had described a gas, normally an ideal gas. So there's an equation. To come up with the properties of an ideal gas, to find out or to calculate the properties of an ideal gas. There's an equation referred to as the ideal gas equation. There's an equation referred to as ideal gas equation or ideal gas law, which can be used to calculate or find out the properties, some of the characteristics of an ideal gas. So when it comes to a gas, what are the properties which explains the behavior of a gas? Right? Few properties are there to explain the behavior of a gas. What are those? The pressure of the gas, the volume of the gas. Normally the volume is the container, the volume of the container, and number of moles of the gas, the amount of gas, number of moles, and the temperature of the gas, Actually, these 4 properties are related by an equation called the ideal gas law. Right? That is this. PV is equal to nRT. This is the equation which relates these four properties of ideal gases. The pressure of the gas, the volume of the gas, that multiplication is equal to the amount of the gas in terms of moles into R, which is a constant, which is known as the universal gas constant. The R is a constant which is known as the universal gas constant. The value of that is actually 8.314 joules per Kelvin per mole. Right, into T. This is the absolute temperature. Here we have to substitute the absolute temperature, the Kelvin temperature. Right, not the Celsius temperature, but it should be the Kelvin temperature. So its multiplication of nRT will be equal to the multiplication of PV. So this equation represents the relationship between the pressure, volume, number of moles and the absolute temperature of an ideal gas. And this equation is referred to as the ideal gas equation or ideal gas law. Right? So in your note, it is said that the absolute temperature, pressure, volume and the amount of moles of a gas are the factors that affect the behavior of a gas. For an ideal gas, the PV, T and N are related by the ideal gas equation. Right? The idea is clear. Right? Okay. So this is also referred to as the equation of state. This describes the state of the gas. This describes the energy of the gas actually. Energy state of the gas. Now actually this is a kind of an energy equation, right? This is kind of an energy equation. If you need to know, see the dimensions of this one, see the dimensions of this side, right? So N means moles, number of moles, R comes up with joules per Kelvin per mole, T comes up with Kelvin, just refer the dimensions, units of this part, right? This is moles to mole minus 1 cancel off, Kelvin minus 1 to Kelvin cancel off, you will remain with joules. Joules means that is the units of energy. So this is actually an energy equation. Because nRT, the ideal gas law, is kind of a energy relationship, right? So at this side, if energy is appearing, this thing also should comes up with the energy according to the unit and dimensions, right? Okay. So this is the energy equation, an equation of state, right? So describes the state of the gas, energy of the gas as well, right? No? Okay. Right. Then in your note, there is a little wording, little sentence, right, after this equation. Let's discuss a bit about that thing. Lamai, if a question is asked like describe an ideal gas, define an ideal gas. If such a question is asked in your exam paper, define an ideal gas or explain an ideal gas, describe an ideal gas, define an ideal gas. If such a question is asked in your paper, right, you have two methods to come up with a complete answer. You have two ways of coming up with a complete answer. One such a way is described earlier. Those 5 points should be written. That is one way of coming up with a correct answer, complete answer. The second way of coming up with a correct answer is the statement appearing after this equation. What is that? You can define an ideal gas like this. This is the short and sweet description of an ideal gas. Short and sweet description of an ideal gas. Earlier was the longer description. So what is the short and sweet description? We can say, if a gas follows the ideal gas law, or the PV equals nRT equation under any temperature pressure conditions, under all the temperature pressure conditions, such a gas is referred to as an ideal gas. If a gas follows the PV equals nRT under every pressure and temperature conditions, such a gas is referred to as an ideal gas. So with that manner as well, you can define an ideal gas. It is a short and sweet description, so which is written after the equation in your note. Go through that. Is clear? No? The gas follows the PV equals nRT under all the pressures and temperature conditions. Is referred to as an ideal gas. Right now? Okay, the things are clear. Right. So let's try to come up with very simple derivations with the use of this equation. Some derivations for concentration of a gas as well as for the density of a gas. Right? Let's try to come up with some equations with the use of the ideal gas law. Right. Let's try to come up with an expression for concentration of a gas. Concentration of a gas. Now actually what is referred to as the concentration? Concentration is the number of moles of gas particles in a unit volume. Number of moles of gas particles in a unit volume is referred to as the concentration of a gas. Let's try to derive an equation for that. So we know that PV is equal to nRT. Right? Concentration means number of moles in unit volume. That means moles per volume. NOV. NOV is considered as the concentration. So we can come up with this NOV if you have to put this V here. So P is equal to N over V RT. So instead of N over V, we can write the C, the concentration. So P is equal to CRT. P is equal to CRT. So this is the relationship between the concentration and the pressure of a gas. This is the relationship between the concentration and pressure of a gas. P is equal to CRT. So actually, pressure is a measure of concentration. Pressure is a measure of concentration, right, of your gas. Pressure is a measure of concentration of your gas. P is equal to CRT. Clear? No? If you are dealing with a constant temperature, say you are thinking of some room temperature conditions, so pressure is a measure of concentration of your gas. If the temperature is a constant, the RT is going to be a constant. That means P is proportional to C. If this is a constant, we can come up with a proportional sign here. P is proportional to C. So when the concentration increases, pressure increases. When the concentration drops, pressure drops. So pressure of a gas is a measure of concentration of a gas. Right? Normally with liquids and the solutions, right, we look for the concentration, for the strength of the liquid and a solution. Right? But when it comes to gases, we define the strength or discuss the strength of the gas with the pressure. Right? So actual pressure is same as the concentration when it comes to a liquid. right? Okay, the idea is clear. Pressure of the gas is a measure of concentration of a gas. So you can complete this stuff, right? Okay. After this, let's derive a equation for the density of the gas. This is clear, no? Let's come up with the equation for the density of the gas. Right? Density of a gas. What is density, Lama? All of us know density is MOV, mass per unit volume. Density is the mass per unit volume, right? That's the density, right? Let's try to derive a equation for the density of a gas. See, starting with the P equals nRT. We know PV is equal to nRT. It is the ideal gas law. So to come up with the equation for the density, first we need to introduce this m to this equation, right? We know that moles can be calculated by, right, dividing the grams by the G mole minus 1 value. So the G will cancel off and comes up as moles. That means N is equal to M over capital M, mass over the molar mass, right? So instead of the number of moles here, you can use the M over capital M. So we can write PV is equal to simple M over capital M RT. So now we can come up with the M over V to find the D. So I just get this M here and put this V down here to come up with the M over V. Right? So this M over V is D. M over V is the density. Right? This leads us to this equation. If you are to subject the D, if you are to subject the D, density, you can write it as D is equal to Pm over RT. Pm over RT. D is equal to Pm over RT. This will Pm over RT. Clear, no? Right? So you can complete this stuff. An equation for the density of a gas in terms of pressure and temperature. Lamai, when substituting numbers to these equations with the R, when substituting numbers to these equations with the universal gas constant, always expected to substitute the values in terms of SI units. In terms of SI units, when substituting the values for this equation, the D comes up as moles per meter cube, moles per meter cubes, moles per meter cubes. The SI unit of volume is meter cubes, M3, right? So mole M minus 3 is the unit for density here for this equation. Pressure is coming up as pascals, the SI unit. Capital M, the molar weight, should not be written as G mole minus 1. The SI unit is kg mole minus 1. The SI unit of mass is kilograms. So the M should be substituted as kg mole minus 1 when substituting this equation. R is with the normal units, right? 8.314 joules per Kelvin mole, and T should be come up as a Kelvin temperature, substitute in Kelvin, right? for any equation containing the universal gas constant R, you should substitute the numbers in terms of SI units. Keep that in mind, right? Even for the earlier equation, the P is equal to CRT, there also you have to substitute the values in terms of SI units. Pressure in terms of pascals or Nm minus 2. Concentration in terms of moles per meter cube. Moles per meter cube. The volume will be written as meter cubes in SI units. And T is in terms of Kelvin, right? So for any equation with the appearance of R, the universal gas constant, should be substituted with SI units. Well, should be substituted with SI units. Clear? Right. So you have some questions there at the workbook. Just do them. At the page number 2 and 3, some questions are appearing. Question number 2 and question number 3 are regarding these two equations, the concentration equation and the density equation. Let's go to that. Right? Okay. Let's quickly come up with the next one. Right? The diffusion of gases. Diffusion of gases. Diffusion of gases. Diffusion of gases. Diffusion means what? Movement of particles from a lower concentration to higher concentration. Movement of particles from higher concentration to one can say higher density. The concentration means same as the density, right? More the concentration means more number of moles in a unit volume. That means more number of moles means more number of particles are there. More number of particles means more the mass there in unit volume. So that is density, right? So higher the concentration means higher the density, right? So movement of particles from higher concentration to a lower concentration. Is referred to as density. So density depends on the concentration, or one can say density depends on the diffusion rate. Diffusion depends on the concentration, or one can say diffusion depends on the density. So we can write the diffusion rate. For the diffusion rate, we come up with this kind of relationship. The diffusion rate is proportional to 1 over D, 1 over density. Diffusion rate is proportional to 1 over density. That is clear, Lama? So if you are to picturize this thing, it's like this. Say you have a system with greater concentration or greater density, or you are with a system like this. So you are expected to move a particle from here to here. Diffusion, right? Moving a particle from one place to another, right? So moving the particle from here to here is easier compared to moving the particle from here to here, right? Because lower the concentration, lower the density, that means more free spaces are available, so it is easy to travel for this particle from here to here. So diffusion rate, diffusion is easier here, diffusion is greater here, diffusion is harder here, right? So diffusion is high when the density is low when the density is low. Diffusion is low when the density is high. So inverse relationship with the diffusion for the density. So we can come up with this kind of relationship. It is inverse, right? Okay. So ultimately we can write by substitution the equation for D here, substituting for D will give you the D is equal to PM over RT. No? 1 over D means RT over PM. So for the diffusion rate, we can come up with this kind of equation. Right, this kind of equation. So this says greater the temperature, greater will be the diffusion rate. It is very clear. Greater the temperature means greater will be the kinetic changes of particles. Greater will be the kinetic changes of particles. So greater the temperature, greater will be the kinetic changes of particles. So it is easy to move from one place to another place as you are with greater kinetic energy. That is what it says. Greater the temperature, greater the diffusion rate. And on the other hand, greater the mass, lower will be the diffusion rate. Inverse relationship. Greater the mass, lower will be the diffusion rate. It is very clear. Greater the mass means you are heavier. You are heavier. Heavier means your thermal motions are restricted. So it is very easy to move a lighter particle than moving a heavy particle. So lighter you are, it is easy to move from one place to another place. More heavier you are, it is hard to move from one place to another place. So heavier you are, hard to move from one place to another place. So that means diffusion becomes harder. Heavier you are, diffusion rate is lower. Idea is clear? What about the pressure? Pressure represents the concentration of a gas. Pressure represents the concentration of gas. Greater the concentration, that means greater the pressure, diffusion rate is low. Lower the concentration, that means lower the pressure, diffusion rate is high. Inverse relationship is there. Right? So when the pressure is high, diffusion rate is low. Pressure is high means greater the concentration, diffusion rate is low. Idea is clear? So you should be able to copy that idea as well. Right? That is clear, no? Okay. Right? Let's move to the final section of this session. Right? The final section of this one. So calculations involving P equals in R. That is what we are going to discuss now. The calculations involving P equals in RT. Right? Right. Calculations based on P equals in RT. Right? When regarding calculations, when we come up with the calculations, right? The first thing to note that is, even though this equation looks like a 5-term equation, an equation with 5 terms, still this is referred to as a 4-variable equation. 4-variable equation. This is a 4-variable equation, right? PV is equal to nRT is a 4-variable equation. It's very important to note that. What are the 4 variables? P, V, N, T. Those are the 4 variables of this equation. Even though it is with 5 terms, just see this one as a 4-variable equation. If you are to see this equation like that, it is very easy to solve the questions involving this one. Right? Why is that? Because R is always a constant. R is always a constant. We always know that value. We always know the value of the R, which is 8.314 joules per Kelvin per mole. We always know that value. Always that is the value we substitute as R. So this is a constant. So only 4 variables are appear with this equation. If you know about 3 variables, if they have provided some data about 3 variables, this can be used to come up with the missing variable. That is the total idea here. If they have given you the value for P, V and N, this equation can be used to come up with the T, the missing variable. If they have given you the values for P, V and T, this equation can be used to come up with the N, the missing variable. If they have given you the values of P, N and T, this can be used to come up with the V, the missing variable. If they have given you the values of V, N and T, yes, this can be used to come up with the missing variable P in this case. Right? So always see this equation as a 4 variable equation. That is very important, and it will be very easy to solve if you have to see the equation like that. Right? That's the first thing to grab here. The second thing, when you are using this P equals nRT equation, you are always expected to substitute the values in SI units. You are always expected to substitute the values in SI units. Right? Substitute values in SI units. Always substitute the values in SI units. Then answer will also appear in SI units. Answer will also appear in SI units. It's very clear. Always substitute the values in SI units, and the answer will also appear with SI units. The idea is this. Right? So let's discuss about the conversions here, and then I'll do example to grab the idea. So basically, when it comes to pressure, its SI unit is Pascals, no? So if they have given you the pressure in terms of atmospheric pressure, ATM, right? You have to substitute that value not as XATM. It should be multiplied by 10 power 5 to come up as Pascals. If 5 ATM is the data given for the pressure in your question, you can't apply the 5 ATM to here. It should be 5 into 10 power 5 Pascals. If they have given the pressure as 10 ATM, you can't apply the 10 ATM here. It should be 10 into 10 power 5 Pascals. Always pressure should be applied with Pascals or Newton meter squared. Both are same, right? This is the pressure correction. When it comes to volume, in questions, volume could be given in terms of decimeter cubes or in terms of centimeter cubes. So you can't apply in terms of decimeter cubes or centimeter cubes for this equation. So you have to convert it into the SI unit. What is the SI unit? It is the meter cubes. So converting the decimeter cubes to meter cubes will be look like it should be multiplied by 10 to the power minus 3 as meter cubes. If you convert the centimeter cubes to meter cubes, it should be multiplied with 10 to the power minus 6. This is how the volume conversion should be done. We substitute in the because nRT. What about the temperature? Normally in questions, temperature will be given in Celsius. If they have given the temperature in Celsius, you can't apply Celsius temperature here. The SI unit of temperature is actually Kelvin. So you have to add some 273 to the Celsius value to come up as Kelvin value. So these conversions should be done when applying the values to the P equals nRT. If you are applying the values to the P equals nRT in terms of these SI units, then your answer will also obtain in terms of SI units. That is the idea there. Clear? Right. Let's do a simple example for this thing. Right. It says a piece of magnesium rod is reacted with limited amount of 25 milliliters of 0.1 HCl. Released H2 gas was collected to a 1 liter rigid container and the measured temperature of the gas was 300 Kelvin. Calculate the pressure of the gas. This is what they are saying. See how to solve this one. So the equation is given as magnesium reacting with 2 of HCl to produce the magnesium chloride and the H2 gas. Right? That is the equation given. And what are the data provided? What are the data provided by them? They are providing some data. They are saying some limited amount of HCl. Limited amount of HCl. That means the HCl is going to be your limiting agent, right? That is what it says. HCl is your limiting reagent. Limited amount of HCl is used, right? What was the value there? Right, 0.1 molar, 25 milliliters were used. Right? What are the other data you have given? And the released gas, was collected to a 1 liter vessel. So H2 was collected to a 1 liter vessel. 1 liter vessel. 1 liter means 1 decimeter cubes. Right? Liters are equal to decimeter cubes. Milliliters are equal to centimeter cubes. Right? Milliliters are equal to centimeter cubes. Liters are equal to decimeter cubes. Right? 1 liter vessel, and the temperature is 300 Kelvin. And they are asking us the pressure of the gas. The pressure of the gas is asked. Let's try to solve this one. Right? See how to approach this kind of question. Get the approach to this kind of question. Right. So first thing in solving questions is actually identifying the goal. Right? What is the goal here? Yes, this is the goal. Nah? This is the goal. Identifying the goal. This is the goal to achieve. Our goal is to come up with the pressure of the H2 gas. And we know we can apply the PV equals nRT, the ideal gas law, to come up with the pressure. Right? We can use that tool, the ideal gas law, to come up with the pressure. But we have a problem there. What is the problem? P equals nRT is a 4-variable equation. It's a 4-variable equation. To come up with the pressure, to find the pressure, first we should know the other 3 variables. What are the other 3? Volume, temperature and moles. We should know the V, T and N. V, T and N to find the pressure with the use of P equals nRT. In this case, B is there, T is there, but we don't know the N. So before applying the P equals nRT to come up with the P, first we need to find the N. First we need to find the number of moles of H2 gas. So we should plan to come up with the number of moles of H2 gas. How to find out the number of moles of H2 gas? How we can do so? So some data are given. Here with HCl. CV data are given. Concentration and volume are given. So the CV values will lead you to number of moles of HCl. If you multiply the concentration by its volume, the CV value will lead to the number of moles of HCl. As this is a limited reagent, we can use the stoichiometry of the limited reagent with the needed one to come up with the number of moles of the needed one. So these two guys will give you the number of moles of HCl. As the stoichiometry between the HCl and the H2 is actually 2 to 1. So number of moles of H2 is going to be the half of the moles of HCl. It's 2 to 1. So CV data will give you the number of moles of HCl. The number of moles of H2 is half of that. So that means the N value, the number of moles of H2, N value for H2 is half of the number of moles of HCl. So that we can find the N like that. We can find the N of the precursor in NRT like that. So if you know the B, T and N, then you can apply the precursor in NRT to come up with the pressure. That is the way of solving the question. So I'll just quickly go through the steps, right? So first we need to come up with the moles here, right? So let's write HCl moles. So that is going to be 0.1 molar into 25 centimeter cubes. 25 centimeter cubes means we have to multiply, substitute with decimeter cubes, right? In CV data, right? So that will give you 2.5 into 10 to the power minus 3 moles as HCl moles. So that will lead us to the moles of H2. So H2 moles. (2.5 into 10 to the power minus 3 is actually representing two portions. Number of moles of HCl representing two portions. We need such one portion. So for two portions, it is this value. For one portion, we need to divide that thing with 2. For one portion, this is the value, right? Okay, one portion. So number of moles of H2 is going to be 1.25 into 10 to the power minus 3 then. This is actually the in number of moles of H2 we need to substitute the precursor in RT, right? So let's copy the precursor in RT with the use of this, right? So I'll apply here. For H2 gas, let's apply the PV is equal to nRT, right? Pressure, that is what we need to find. B, volume is 1 decimeter cubes. We can't apply the value in decimeter cubes. It should be applied with the SI units, that is the meter cubes. So 1 into 10 to the power minus 3 meter cubes. N, number of moles, yes, we have found that thing, 1.25 into 10 to the power minus 3. R is the 8.314 joules per Kelvin per mole, and T is what? T is 300 Kelvin. Always substitution should be done with the SI units, right? Okay, so let's try to simplify this one. So you have a P, 10 to the power minus 3 is there, and 1.25 into the power minus 3 is there. Lamai 8.314. For the easiness of simplifications, we can apply 100 over 12 instead of 8.314. Lamai 100 over 12, that gives you a value like 8.33. 100 over 12 gives you a value like 8.33, right? But for these calculations, we are expecting your answer to the first decimal. That is enough. The answer to the first decimal is enough, right? So that we can apply for this first decimal, this is enough. Instead of 8.314, we can apply this 100 over 12. So and 300. Just simplifying, right? So these things can be cut off, right? Some 4 appears here, right? Then it's like, so 10 to the power minus 3 cancels off from both sides, right? So it looks like P is equal to, so it is going to be, right, I'll just 1.25 divided by 4, that means 0.31, right? 1 is remaining, 25, no? Into 10 to power 1, 2, 3, 4, 10 to power 4. This can be simplified as 3.125 into 10 to power 3. Right? This can be simplified as, coming up with one decimal here, right? So 3.125. 3.125 into 10 to the power 3. And what is going to be the unit? It is the SI unit. This is the SI units. No need of simplifying the units here. As long as you are substituting with SI units, the answer comes in SI units. As long as you are substituting with the SI units, answer come in SI units. Right? So when applying the P equals nRT, these are the marking points. Coming up with the correct equation, substituting with the correct units, and the final answer with the correct units. So those should be written properly. Right? As far as you are substituting with the correct units, SI units, the answer comes as SI units. No need of cancelling of the units, right? Easier like that. So this is how we are supposed to solve the question number 1. Right? Just do this simplification so that it is very easy to come up with the answer with this simplification, right? Applying the 100 over 12 instead of 8.314. Right, no? So the things are clear, right? So this is how we are supposed to solve the question number 1. So question number 2, 3, 4 are appearing with your note, right? At the page number 5, question number 2, 3, 4 are appearing. Just do those at your home as homework, right? Okay, I'll send you the answers, but just do the stuff as homework, right? Okay, so for today, that's it. We'll meet with the next lesson next week. Until then, goodbye.